Okay, so hello everyone. Let's start the session for today. So let's start with that. Okay. Hello engineers, welcome back to the fourth session of the ROS Learning Series. In today's session, we are going to discuss and as well demonstrate. We are going to create a custom mobile robot and simulate it in ROS. In the previous session, I told that we were going to simulate a robot arm in the next session, but the mobile robot is would be a bit better for the learning perspective, as well as we would get to know how to create a robot in ROS and simulate it as well. So let's start with it. Okay. A quick recap before we start with the session. In the first session, we have installed ROS. We have simulated the TurtleBot 3 robot, and we have discussed the main three components of mobile robots, which are localization, mapping, and navigation. We have also discussed the different ROS concepts and the different commands that are used to run and launch different launch files in ROS. So we have an introduction to ROS. So in today's session, we are going to create our own custom robot and see what it takes to do so. So let's get started. Okay, so the first thing that we need to do to simulate a robot is to model it in some way. A common method that is used to model robots in physical terms is using this link and joint terminology. Joint is simply a part that moves like the motors or actuators, and link is a part that connects two successive motors or joints. This link and joint based modeling can be used to represent any form of robot that we usually see. We have here four examples that we can discuss how the link and joints are made in this. For the robot arm, the links and joint connection is a sequential one in nature. We have a link, then we have a joint, a link, a joint, and then link, and so on. So this is how how a robot arm is physically modeled. And the second over here we have is the mobile robot. Here also the wheels are the joints and the whole body of the mobile robot is the link. We can also see that here we have labeled a fixed joint. A fixed joint is simply a joint that does not move. That's a special case of a joint, and that joint is used to connect the LiDAR sensor with the robot base. So as we can see, the link joint terminology holds here as well. If we consider a quadruped robot, then the joints are in its leg joints, as we can see over here, two joints in each leg, and the rest of the body is connected using links. The same goes for a quad rotor or drone as well. The joints are the propellers that spin and make the robot fly in air, and links are the connections that are between the joints, the quad rotors or drone's body. So we can see we can just by changing the sequence of joints and links, we can model any robot we can think of. So the joints can be of different type. Before we saw that we saw a special case of fixed joint. Joints are made of many types, but for our purpose, we are only going to discuss four. And for the complete session, we are only going to use a single joint, which is the continuous joint. So let's discuss what are these joints. A revolute joint is simply a rotation joint. We can imagine this like a door joint, like the door only rotates about a fixed axis. So a door kind of mechanism uses a revolute joint. One key thing to note is that we can also see this in a door, that we have a limit up to which we can open the door and we can close the door. So a revolute joint has a maximum or minimum limit attached to it. Second is the prismatic joint. A prismatic joint can be imagined like a syringe we have. In a syringe, when we press the piston, we can say piston, then the motion only occurs in a linear fashion. That kind of motion of joint is referred to as a prismatic joint. Third is the continuous joint. A continuous and revolute joint, in motion wise they are similar, but a continuous joint does not have any limits attached to it. It is, we can imagine like a wheel of a car. It can rotate. It is a rotatory motion, but there are no limits as to how much the wheel can rotate. So that's a continuous joint. A fixed joint is a joint that is fixed and does not move. we can say that it is a type of joint that does not allow any form of motion as such. So these are the 4 joints that we have. Throughout our session, we will be using to simulate the robot, continuous joint and fixed joint mainly. Okay, so let's discuss some. Okay, now we know how do we physically model the robot using links and joints, but we need to represent the robot mathematically as well in order to uh, have a concrete view. Now the mathematical description of different robots is done in a bit different way. The main concept used is coordinate frames. The coordinate frames, we attach these coordinate frames to different parts of the robot to represent the robot mathematically. The first thing that we need to do while simulating any robot is to assign a world coordinate system. This is the origin system, as we can see over here. It is the origin system that is used to represent everything in the world or in the simulation. It can be points of interest. It can be the points that a robot has to reach. It can be the point the robot has to start, and it can also be the point where the robot is situated. All of this is represented with respect to the world coordinate system. Next system that we set up, the next coordinate frame, is the base coordinate frame, as we can see over here. This base coordinate frame is responsible, or it helps us to represent the robot better. Using the world coordinate system, we would first have to transform to the other coordinate systems to see how the robot is moving in the world. But to see everything with respect to the robot, we use this base coordinate frame. That's the idea. Now for the robot arm, the further coordinate axes are placed at the joints, as we can see over here. The first joint is a rotation joint that we can see over at the base of the robot. The second is also a rotation joint. A coordinate frame is fixed to this. To the third joint, a coordinate frame is fixed as well, and it just goes on until we reach the tip of the robot. Now, these coordinate frames, we attach these coordinate frames to each of the joints. If we go rigorously behind the mathematics that goes on, then there are certain rules as to how we are required to assign these coordinate frames. A simple coordinate frame has x, y, and z axis. Now, if we go as we rigorously mathematically, then the direction of x, y, and z are fixed if we go by that. But since we are simulating, any arbitrary direction of robot motion can be chosen. For instance, over here, as we can see that they have fixed a z-axis about the axis about which the motor motion will take place. As you can see, about the z, this motor will be rotating. In a simulation, there is no particular requirement that we have to put it on z. It can be on any axis as long as we are completely comfortable with it. So to summarize, to represent a robot or a robot arm, first we fix a world coordinate system, then we fix a base coordinate system, then we assign coordinate systems to the robot joints. And this is how we can mathematically represent a robot. Now the use for this, I will cover this as we go along the session. First, let us discuss how the coordinate frames are set up on a robot. Now for a mobile robot, the coordinate frames are fixed just such as we have a coordinate frame, base frame at the robot body, and we have this world frame. Then there is also a coordinate frame that is fixed to the sensor, to a sensor of the robot, as we can see over here. There are coordinate frames that are fixed to the wheels as well. These are the motion ones, as we can see over here. Okay, so over here, the RGB represents R is X, G is Y, and blue is the Z axis. So over here, the green or the Y axis is is how the motor motion is going to be going on for the wheel. It's going to be about the Y axis. So this is how we set the coordinate system for a mobile robot. A drone is also similar. We'll not go into much detail. We have a world system and we have this base system, and we also assign coordinate frames to the propellers as well. And that's how we model a quadrotor. Okay. Now to how we are going to model the model that we discussed mathematically, how we are going to represent it in a computer simulation. Now ROS uses a particular file format which is URDF, Unified Robot Description Format. It is simply an XML file that is used to describe the relations between the different joints and links. Now over here, as we can see, if we have a link, let's say name it link 1, then it's connected to joint 1 and joint 2. Then these joints are further connected to further links and further joints and links. Now in the XML format, what we will do, the first link that we have will be set the parent link, and the parent link is joined to a child link through a joint. So this is how the URDF file, in the URDF file, we are going to describe how the relation between parent and child is, and that is going to create a simulation for our robot. We will discuss its example later as well when we move on to the demo. Now the URDF file helps us to describe 3 parameters, which are collision, visual, and inertial. Now visual is responsible, as the name suggests, it is how the link is going to look like what is going to be the shape of the link. It can be a mesh file, an SDF file or something like that, or it can be an easy cylinder type of body as well. Next is the collision. Now collision, as we discussed before as well, that Gazebo is a physics simulator. To simulate the robot in a physics simulator, we need to do collision handling. Now collision handling is done using this collision property that we will set in the URDF. Usually this is exactly similar to the visual one. If the visual is a very complex kind of shape, like a lot of different curves, then we usually simplify the collision to just be a cylinder type of thing. If the visual is already a simple shape, then the collision is also taken to be the same shape. Okay, the next component that we have is the inertial. Now inertial is responsible for the mass handling and what are the different calculations related to mass and inertia of the robot. This we have to set. We are not going to discuss much. This we just have to set in the simulation to run the simulation well. Okay, now what was the thing behind the coordinate frames that we set? Once we set the different coordinate frames, the next step is to transform between these coordinate frames. Now, if we know the location of the world, then we need to know what is the location of the laser, what is the location of the IMU, and what is the location of the camera. So these are actually derived. These are very simple matrix-based multiplications that we have to do to transform between one frame of reference to another frame of reference. What ROS does is we do not have to code these mathematical relations from scratch. ROS provides us a package called the TF package, which automatically does these calculations for us. So we just have to provide these coordinate frames, and ROS will take care of the rest, how to transform between the different coordinate frames. Now, why we need these different coordinate frames and why we need the transforms? One very basic idea is that ROS uses these coordinate frames to reconstruct the complete robot. Let's say, for instance, the ROS does not know the transformation between camera and IMU. Then ROS is going to give an error that it does not know the transformation of camera, and it will not be able to represent it in the simulation. That is one use case that we have. Another second use case that is a good use case, I would say, that is for some algorithms like sensor fusion. Now let's say that we have a mobile robot and we have two sensors that are placed on it. First is the laser and second is the camera. Now let's say that the mobile robot is seeing through its laser that it sees a gap somewhere, that there is no obstacle and there is a path that it can follow. So it sees that through the laser readings that are coming. It also sees the same observation using the camera, that it does not see any obstacle and it sees a straight path ahead. To increase the reliability of the sensor. Now sensor values can have an error up to certain limit. So to create a reliability system, we use an algorithm called sensor fusion. As the name suggests, we are going to fuse the sensor values coming from the different sensors. For instance, we are going to combine the the camera image that we had and the laser scan that we had to get a final reading that will be more accurate, as the errors will be averaged out and cancelled. Now, to do that sensor fusion, we need to see with respect to the laser frame as well as the camera frame. With, for instance, in a mobile robot, the laser can be a bit at a lower position and the camera can be at an upper position. So to fuse the sensor values, we need to adjust with respect to both these coordinate frames, how the camera is seeing the world and how the laser is seeing the world. So that is another use case of the transforms and the coordinate frames. It's used in most of the robotics algorithms. So it's a general concept applicable in all of robotics. Okay, now we have simulated the robot. Let's say that we now we have the tools that we need to simulate a robot, how the robot is going to look, how it's going to collide, and so on. But to move the robot, there is another component that we need, that is the controller. A controller is responsible for doing the different mathematical calculations to determine how the robot is going to move. If the robot moves, what is it going to be its next position and velocity and so on. To handle all these calculations, there exists a concept called controllers. Now, since we are only going to discuss the mobile robot controller. So the mobile robot that we are simulating is going to have two motor wheels, as we can see over here, and a caster wheel, which is just a supporting wheel to support the complete structure. Now, this kind of robot structure is called a differential drive robot structure. To control or to move the robot with respect to this architecture, the controller used is called a differential drive controller. Now, when we apply a velocity to one of the motor wheels, then there are going to be certain mathematical formulas that are going to tell us where will the robot be after some t time interval, as we can see over here. Now, these are more or less complex calculations, but since we are using ROS, we are not required to write these different mathematical relations. ROS will automatically provide us with a pre-built or pre-code controller, the differential drive controller. All we have to do is set the different parameters of the controller, like the distance between the wheels, the diameter of the wheels, and so on. Then using these variables or values, the robot will be simulated and it will be controlled quite easily compared to writing the complete code from scratch. Okay, so these are all the components that we have to simulate a mobile robot. The mobile robot that we're going to simulate today is a robot that is going to look like this. This is, for reference, this is the tortoise bot, which was the first mobile robot that was developed in the 1940s or so. This was made by by a person named Gray Walters, and this was the first robot. It was named, I think, Elsie. The purpose of this robot was to move around the environment, and it responded to photo or light sensing. So based on where the light was coming, this robot used to follow that. So this was one of the first mobile robots, and we are going to try and simulate this robot. We are going to create this robot from scratch. Okay, so we will be moving to demo. If anyone has any questions, then they can ask. Okay, no questions. So let's start with the demo. Now, first thing that we are going to do is start the LX terminal. Okay. Now, to simulate or create the simulation of a robot, the first step is to create a ROS package. We are going to create our own ROS package, and then we are going to put all of our code in it. Now, let's say that the first step is to go to the Catkin workspace and then go to the SRC directory. If we do ls, then you can see that we already have a lot of different packages, the turtlebot 3 packages from the previous sessions. I also have this tortoise bot package as well, since I have already coded the examples that I'm going to show. Now to create a new package, the command is catkin underscore create underscore pkg. Pkg stands for package. And then we can name the package what we want. Let's say that I want the temp package. That is the name that I want to select. Then we will press enter and it will automatically generate a new ROS package for us. Now let's see what is inside this ROS package that it created. So it's just a directory that the ROS system has created for us. And if we do ls, then we can see that there are two files in this. The first is cmakelist.txt and the second is package.xml. Now we do not need to worry about the cmakelist.txt. It's usually, especially in ROS1, if we write our code in Python, then we do not need to make changes to the CMake list too often. This is usually more used when we write our code in C++, since this describes how the building of the code is going to take place. So that's what the CMake list does. However, just to point out that in ROS2, Python codes are also compiled. So that's why over there we have to adjust the cmake list.txt for Python files as well. Not required for ROS1. We are discussing ROS1, so no requirement to be changed. Second is the package.xml. Now this file describes what are the different meta information related to the package, like who is the maintainer of the package, who is the developer, what is the name of the package, what is the description, and so on. In addition to that, it also describes what are the different prerequisites to run this package. For instance, for our package, there can be like, we need the tf ROS package to run. So we will write that in package.xml. But usually ROS provides us with the tf package, hence we are also not going to change this too much. If the project is big and we use a lot of different ROS packages that are not by default installed, then we usually make changes to the package.xml. Okay, now before we make changes to the different files over here, we need a text editor. So you can install any text editor as you like. As we can see in the Ubuntu system that we have installed over here, we also have the different browsers. You can just go onto the browser and install any text editor that you like. But for our purpose, I have used a simple text editor which goes by the name of gedit, and you can simply install it using this command sudo apt-get install gedit. I have already installed it, so I do not need to run this again. Okay, now just let's have a look at the cmake lists and package.xml file just to have a look. So the command to run a file is gedit, the file name that we have. I'll just increase the font size. Okay. Right. So as we can see, it is describing the package and product name, then it's saying the find package and all. Like if we are creating our own ROS message, the message component that we discussed in the previous session, the message that goes between the different nodes. If we want to create our own ROS message, then we need to make some changes over here. If we want to, yes, as I discussed, mostly C++ related changes are required in this file. So most of it is commented by default. So we don't need to change it much. Okay, next let's have a look at package.xml. So package.xml is an XML file that describes like the name, the version, the description, the maintainer email, and so on. Over here towards the end, we also have the different dependencies like the built-in dependency catkin. We can define the different dependencies over here, but for our case, we are not going to do this right now. Okay, so we have all the different components now. Now let's create a new file. Okay. Now, once we are in the temp package, then we need to create a folder that goes by the name of URDF. The command to create a new folder is mkdir URDF. So we create that and then we do ls to see that we have a new folder by the name of URDF. Then we navigate to the URDF folder. And now we want to create a new file. The command for that is once again gedit. Now the file that we wanted to create was tortoisebot.urdf. So this is the command that we used to type to create a new file. Now once it is created, now if we save this by pressing the Control S, it's going to save the file in the original directory as well. Let's just start with something. So we have this file and I have saved it as well. If we close it, and now we can see that we have the tortoiseboy.urdf, and if we want to open it, then we have to use the same command. So we have it over here. Okay, so this is the way to create the new different files. Now the rest of the files that I will be discussing, these are in the slides as well. You can check them when you would like. I have already written the code for this. We are just going to have a look at what is present in the code files. So I'll just navigate to the already written code files that I have. Now the package that I created already was named tortoiseboy. You can name it any package as you want. So we will go to the URDF folder, and over here, what I have done is that created a number of different files for each set of slides that we're going to discuss. Like the one slide over here, the code for that over here is your tortoisebot1.urdf. So we are going to have a look at that first. Okay, so the first thing that we need to write in our code is this question XML version equals 1.0 question closing angular bracket. This is a optional thing that we want to write. This simply tells the editor, the text editor that we have, that we are going to write an XML file. This is completely optional. If we remove it, then it's going to not change anything. The next part that we have over here is the robot tag. Now the robot tag has this attribute name, and we are going to set this to the robot name that we have. Then we close this robot tag as well. Inside this, we are going to create our first link, and that first link is going to have its name base link. So we create the tags for that as well. Now, for the initial few slides that we're going to discuss, we are only going to define the visual component of the URDF. Rest ones are we are going to derive it as we go along. We first want to see how the robot is looking. That's why we are only considering the visual tags for now. So we define this visual tag, and inside this we have this geometry tag. And inside the geometry tag, we have the box size. Now, there exist other different tags as well that we want for different shapes. This is for the box shape. If we want the cylinder one, then I think it's cylinder or something like that. And we have to set it to R and D, R and H. Like we have the different attributes that we have to set, the radius and the height that we want to set. And it will create a cylinder for us. To check what are the different shapes that we can, you can simply Google that, and Google will quickly show the results of what are the different shapes that we can draw. For now, we only require the box, and we are going to put that. Then we define another tag material, and in this we are going to apply a color to that link that we have. So we're going to apply this 0.75, 0.75, 0.751. Okay, so once we have this file, once we have created this file, we are going to open our terminal. We are going to go to the, okay, one thing to note is that we do not want to close this terminal. Otherwise, the gedit program will also close. That's one thing. So we first navigate to the Catkin workspace, and the first step we do is source the workspace. That is the first step that we always do. And then we are going to navigate to the tortoisebot file that we have in the URDF. We have this file in the URDF folder. And now we are going to run this command, ROS launch URDF tutorial demo.launch. And then we have, okay, URDF tutorial display.launch. Then we have whatever is the file name, we just have to type that file name in this command over here. So let's run this, and it will start an RViz visualization in which we would be able to see our robot. Okay, for now we have only created a single link, and that is why we are only seeing a single link, which is the box. Simple. Okay, now we'll close it, and now we are going to add other components to this. Now I have written this in tortoiseboy2.urdf. So we had this link component over here. The next thing that we are adding is the front caster link. This is just a small appendage that will be added to the front of the robot that will contain the front caster wheel. So we first create the link and then we adjust its dimensions. Now, one thing to note, once we named the material and we adjusted its color property, next time when we want to use this same material, we only call this material tag over here. We do not need to again rewrite the color RGBA as we wrote before. Now, once we have two links, now we need to connect these links using a joint. So a joint will come in and connect these two links as we discussed before as well. So to create a joint, we have this joint tag and we have this attribute name. And then we set the type. Over here, we are setting the continuous type. We could have set it revolute, prismatic, and so on. But for our case, we are going to set it to continuous. Then we set the axis about which the rotation is going to take place. For our case, we want the rotation to take place about the z axis. Then we set the parent link, which is the base link. And then we set the child link, that is the front caster link that we defined over here. And then we have this origin. RPY stands for roll, pitch, yaw. This adjusts the rotation of the coordinate frame. And XYZ is responsible for translating the coordinate frame over different locations. Now, we need to understand this. How are these parent and child links related? Let's say that the base link, okay, so let's consider the parent link, that is the base link. So the base link is going to be created at the origin by default. So the ROS is going to create a base link at the origin. Now, this 0.3 over here simply suggests, let's say this is the x-axis. Then with respect to this x-axis, it's going to move 0.3 in the x-axis direction. Once it reaches over there, then it is going to create the child link, that is the front caster. So that is the relation between the parent and child. With respect to parent, we set the joint location using the XYZ and RPY. And with respect to that, after we translate and rotate to that point, then we create the child link over there. Let's simulate this and understand it visually as well. So we first simulated that. Now we're going to simulate the tortoiseboy2.urdf. And another thing that we are going to add to this command is a new parameter GUI equals true. Okay, so let's see it over here. This we have the base link, which is made at the origin. Now it moves 0.3 in the direction of x-axis, and then it creates the child link. So that is how the creation process goes on in ROS. When we are going to define complex parameters for RPY and XYZ, that is the complete procedure that is taking place behind the scenes. Okay, apart from that, we set the GUI equals true, and that is to show this small window over here. This is just a slider that we can move to see how the joint is moving. As we can see, it is rotating with respect to Z axis that we set over there. The limits over here are to just demonstrate. Otherwise, there are no limits on the continuous joint. Okay, so it can move. We are sure of that. All right. Now let's open the next file. All right, so we already have placed the link and the different and the joint. Now we are going to add the wheels to the model. So for that, the commands are almost similar. We first add a link. We first add a link tag with the name, and then we add the visual tag. And over here, we are defining the cylinder shape. For cylinder, we have two components, which are the length and the radius. These are pretty much, I think, obvious that length is the height and radius is the radius of the cylinder. And we are creating a new material by the name of black, and which is has the RGBA component 0001. Then we create a joint for that link. Now with respect to the front caster, we are setting the front wheel. We are rotating that roll with minus 1.57, and we are setting the XYZ to these values. Just to keep it clear, RPY stands for roll pitch yaw. This simply means that we are doing rotation about the X, which is the roll, Y, which is the pitch, and yaw, which is the Z. So it's just rotation about these three axes. That's what roll pitch yaw describes. And then we add this right wheel as well. And for that, this right wheel, we create a joint, right wheel joint, and the parent link is set to base link. We also create the left wheel, which is just symmetrically opposite to the right wheel, and the different components are seen over here as well. The code for this is in the slides that you can replicate. Okay, now let's run this file now. Okay, now we have the different components over here. We can see that we have three wheels now, and we can rotate these wheels if we want. Like, as we can see, the wheels are rotating once we change the slider values. Okay, so this is now done. Let's see the next step. Okay, now we have been simulating this robot in the RWiz visualization, which is only able to show us how the robot is looking. To actually simulate it in a simulator, we need to simulate this in the gazebo simulation. Now for that, we are going to add the different tags. We already had the visual tags. Now we are adding the collision tag and the inertial tag. As we discussed before, since the visual tag is very simple in shape, it's just a box and the rest are just cylinders. We are going to replicate the same shapes over here. We have this box, and further on, we are also going to see that it's just the same for our case. And then we have the inertial tags, and in that we define the mass and the inertia matrix. Inertia matrix is I would say a complex mathematical concept, I would say, for now. So let's just keep it as it is. It's just, we can say, mass. If we want to rotate an object, then what is the mass related to that rotation, in very simple terms. Okay, so these can be calculated using a formula based method. There are different formulas to calculate the inertia, but we have already calculated this and placed the values that are going to be. We do this for all the links that we have. We define the collision and we define the inertial. It's done for all the different links, and I have provided the code in the slides as well. Okay. So next thing that we have to do is create a launch file as well. Now running the RWiz was simple. We already have a launch file that was made to visualize robots. Now we need to create a launch file to run the simulation in the gazebo. For that, we have, okay. Okay, let's say that we are in our package, the temp package that we created, and currently we would have this state of the complete folder. To create a launch file, we first create a new folder that goes by the name of launch. The command for that is mkdir launch. And then we're going to navigate to the launch folder, and then we're going to create a new file that is going to be named tortoisebot.launch. And in this file, now we are going to write the different things that we're going to discuss now. I've already written them to save some time, you would have to write them from scratch. Okay, now let's open this. As we can see, we have this URDF folder and launch folder. And for the particular instance that we're going to run, I have this tortoisebot 4.launch. Okay. Now, by default, we are not going to see this color, as I discussed as well, that if we add the XML version tag, then it's automatically going to show the color. Okay, so the first thing that we want in these launch files is this launch tag. And then we have the different tags in this. First, we set the param tag, which is the robot description, like where to find the robot file. For this particular instance, we need the tortoisebot 4.urdf. As we can see, we first wrote find tortoisebot, the find the tortoisebot package. We're going to write the package name over here. Then we're going to describe the path relative to this package /urdf/tortoisebot. Then we are going to include another launch file, which is the empty world.launch. This is the same launch file that we used in our first session as well. Then we're going to run two nodes. Once. Okay, this is not to be done in this part. We will discuss what was that node in as we go along. For now, for this step of the discussion, we are going to add this node, which is spawn URDF, and this comes from the Github ROS package. What it is going to do, first we set the parameter robot description. We first found the URDF file, and then we are running this node to spawn that robot in the empty world.launch file. And the model we want to set is tortoisebot. So let's run this launch file now. To run this launch file, okay. To run this launch file, it is important that we source as well. So I'll just source it again. Now we are going to type the ROS launch command. Then we are going to type the package name tortoisebot, and we are going to type the launch file name, which is tortoisebot launch 4.launch. And then we're going to run this. So we can see that we have this simulated robot in Gazebo now. If we had not added the different tags that we added, collision and inertia, without the inertia tag, the simulation would work, but without the collision tag, the simulation will not work. That's a thing to keep in mind. Now we have the simulation of it running as well. Let's close this for now. Okay. All right. Now this is the part that we had for the complete physical description of the robot. Now it's time to move the robot as well. To move the robot, we are going to move our robot using the keyboard that we did in the first session as well. In order to enable that keyboard commands, we first need to install a ROS package that goes by the name sudo apt-get install ROS noetic. I'll not write it, maybe. Here it is. ROS noetic teleop twist keyboard. The first step is to install this ROS package so that we can run the different commands using the keyboard. So once that is installed, then we move on to the next step. So I'll open the tortoisebot 5.urdf. So in the previous steps, we have created the complete physical robot. And now towards the end of the file, we add this new tag, gazebo tag. And in this gazebo tag, we add a plugin tag, which has the name attribute differential drive controller. And we are going to specify the file name libgazebo rosdiffdrive.so. These are to be kept same as we have described over here. Then we define the different parameters for this plugin. We set the left joint to the left wheel joint that we made above, right joint to right wheel joint, and robot base frame to base link. Then we set the parameter values of the wheel separation and the wheel diameter. And then we also keep this parameter publish wheel joint state to true. So these are the things that we needed to add to run the robot as well. Now let's simulate this robot again. Yeah. Let's simulate this robot again and run it using the keyboard controller as well. The first step is to source the workspace. Okay, now the command that we need to type over here is ROS run teleop twist keyboard teleop twist keyboard dot py. I'm going to run that. Okay. Now to control the robot using the keyboard, it's I, J, K, L, and M. So using the I button, the robot will start moving forward, and using the K, it will just stop. Using the J and L, we are going to rotate the robot. So it's the structure is similar to a uh, chair that we moving wheelchair that we have. So we can move the robot as we want using these commands. Okay. I'll not close the simulation. We need it for the next step. Okay. Now we have the gazebo simulation running, but we also want the RWAYS visualization to run as well. To run that, we can simply, the command to start the RWAYS visualization is simply we type RWAYS. Either we can run the ROS run RWAYS big command. We can run the small command as well, which goes by RWAYS. The first step is to source the directory. That is important. Okay, so we are going to set this map that is fixed frame to the base link. And then we are going to go to add, and then we are going to add the robot model. Okay, now we are going to see an error over here that we have to fix. Let's see what this error is. Now it says that the error over here is on this front caster and front wheel. What it is saying that there is no transform available from the base link. This is the exact same thing that I discussed at the start as well. Without the transform, ROS will not be able to reconstruct the complete robot. Now the thing is, we do not have the transforms for the front caster and front wheel, which we have to provide. Let's see how we're going to provide that. Let's close this and we will close the simulation as well. Okay, I'll open the sixth file now. Once again, towards the end, now we are going to add a new plugin that goes by the name of Joint State Publisher, and we are going to add the joint names front caster joint and front wheel joint. So what the why ROS was not able to publish these joints that we have specified over here is that the differential drive controller was able to publish these two the transform of these two joints, left wheel and right wheel, because we set this parameter true over here. The rest of the different joints were not being able to publish because they were not specified in this plugin. To run this, we need to make changes that we have applied over here. This is going to publish the front caster joint and the front wheel joint as well. In addition to this, we also need to make some changes to the launch file as well, which I'll describe in tortoisebot6.launch. Then now we have to add this new line, which is node name robot state publisher. Once we add this, the complete transformation will be available to us. Yes. So let's just quickly run this. I close the gazebo simulation for now since we do not require this, and now we are going to add the robot model. And we are going to change this from map to base link. Now there are no errors as we can see over here, and the complete visualization is as we can see. Okay. So one last thing that we now have to do is add a laser sensor to the robot. So let's see how we are going to do that. I have done this in tortoise bot 7.urdf. Okay, so we go to the end. Okay. So just before this gazebo tag, we first have to add a physical link of the sensor. This is done using this link, another link tag. We have this link tag, we name it Hokuyo link, and we define its collision, visual, and inertial. Then we add a joint that connects this Hokuyo link to the base link, and this is a fixed joint. It's going to fix the sensor over a particular point on the base link. Then towards the end, we are going to add a new gazebo tag that has the attribute reference Hokuyo link, and we add the different sensor based tags over here. These are related to the sensor, the laser sensor that we are going to have. Visualize false update rate, and these are going to be pretty much the same, not much to explain over here. Once again, we are adding a plugin that the file name is libgazebo ros gpu laser, and we set the topic name to /scan. This is the same /scan that we discussed in the previous session as well. We have a topic name, and we have the frame name as well, which is the Hokuyo link. Once again, we create a new, okay, let's see if there is a change in the launch file. So launch file remains the same that we have. Now let's run this once. See. Now to check, now as we can see, we have this physical sensor over here. Now to check if it is actually working, it should be working. Let's add a box in front of it. Now when we are running the RViz visualization, we will be able to see what are the sensor readings when this box is placed in front of the robot. So let's first run RViz. Okay, let's change the fixed frame to base link. Then first thing we add is the robot model. And after this, we add a new component, which is the laser scan. In the laser scan, there is an attribute topic over here. We are going to select this and select /scan and press enter. On pressing enter, we can see that the laser values are, as we can see over here. As the box is placed in front of the robot, we can see what are the laser values that are being detected. So this means that everything is working fine. All right, so this is it for the mobile robot that we wanted to create. There is one last step that we have to do. So before moving on to that, if there are any questions, you can ask now. Okay, I'm going to quickly stop presenting. As for the next component, I'll need this and then I'll represent it again. Just a minute. Okay, it's okay. All right. Okay. So I'll be representing it. So the next component that we're going to discuss is related to the relevant assignment for this session. Now, once we have the complete code we have created, now we have to publish this code on GitHub. Now I am going to show the simplest way that we can do this. The first step is to go to this taskbar menu and select any browser that you would like to use. I'm using the Firefox over here. In the next, when the browser opens, we are going to go to github.com. And over there, we can then click sign in or sign up. Sign up if you're first time using that, and sign in if you already have your account. You can use your Google account to link them and you will be good to go. So once you have logged in, you will be in this page over here. I'll just start showing it from over here. So I have this GitHub. This is my GitHub profile that I have. So the first step we have to do is press this new green button. And this will take us to a new page and we have to set the repository name. This is simply the project name that we would like to have. I would like to name it Tortoise Bot. And we can also add a description. So I'll just add the description, Tortoise Bot Simulation. And we need to keep this public so anyone on the internet can see what we have written in the code. If we keep it private, only we would be able to see it. We have to keep this public. Then we can simply tick the add a readme file. This is only going to add a new file readme.md. And we're also going to add the .gitignore. In this portion over here, we are going to add this ros.gitignore version. It's just simply following these commands. That's all. Once we have done this, then we are going to create the repository. And GitHub is automatically going to create this for us. So we have this gitignore file and we have this readme.md. Now to add the files that we just created, we have to press over here, add file button, and we have to click upload files. And then we have to click on this choose your files, or you can simply drag the files that we want. So we will first go to choose files, then over here. Okay, so the thing that we have to push to GitHub is we are going to go to this Tortoise Bot package that you have. And in this package, we are going to select all the files and folders over here. We are going to have two files, package.xml and cmake and we're going to have two folders. We are going to select all of them and click open. Okay. Okay. So it did work before, but it doesn't seem to be working now. Okay, we will try this as well. Okay, I'm just dragging it. Otherwise, it would have worked. If it doesn't work, we can simply drag it. And once I'll just click cancel now. So once we have selected the files and folders, we are going to see these uploaded over here, package.xml, URDF / whatever the files were. And over here, we can add a commit message to tell that what are the changes that we have made. Let's say that I write add tortoise bot URDF files. And we can add an extended description as well to describe all the changes. For now, we'll just keep it empty. And we're going to select this first value that we have, commit directly to the main branch. And then we're going to click this commit changes. So it will take its time to process the files. And once we have processed the files, we are going to have all this available over here. Okay. So once you have this, once you have created this, what I would like you to do is the instructions are the same for this session as well, that you have to create a social media post with the different photos and GIF or videos and so on. In addition to that, you have to copy this link that we have over here, github.com/ whatever will be your username / tortoisebot or whatever repository that you created. You have to put this in your social media post as well. This is just for people to see what is the code that you have written. Since we have made this public, anyone on the internet would be able to see this. Even you would be able to see this even after the session has concluded. So you can just check this link that we have. So you have to do this, and everything is same. Replicate instruction and post on social media, and you have to put that link over there as well. All right, so this is it that we had for this session. And in the next session, let's see if we are able to simulate the UR5 robot arm. And this is it. If you have any questions, you may ask, or we are done for the session otherwise. Yes, we will make dummy as well. I'll stop the recording. Okay, so no sessions, no questions. So we will close the recording and close the meet as well.